Uh, Hello, welcome to the next class. It is class 35, 36, something like that, because there were some classes which I took but didn't record. Anyway, the topic of our discussion today is Grand Canonical Ensemble. These, whatever I'm going to teach, it's there in Rive, but not in the same format as in Patria, Wang, and Kardar. So Huang does it, Rife does it a bit different. So basically, whatever I'm teaching is essentially from Huang, uh, section 7.3. So what we have been discussing till now is the canonical ensemble, and in the canonical ensemble, you have essentially a system with n particles fixed in volume V, and it is in contact with a reservoir. Uh, and there is energy exchange with the reservoir. The bath properties, the reservoir properties decide the temperature T, and in equilibrium, the system of interest, suppose this room, which is in contact with the city of Pune, so the city of Pune being the reservoir. So the temperature of this room or the temperature of the system equivalently maintains the same temperature as that of the reservoir, which means that this room without AC has the same temperature as that of the city of Pune. But practically in this room, what you know is that this room not only is exchanging energy with the reservoir, not only is the system exchanging energy with the reservoir, there can be exchange of particles as well. So particles from the outside, a few can come in, and at a later point in time, a few can go out. So the number of particles in this room is fluctuating. Of course, the average number of particles in this room is fixed, but actually the average number of particles, you can calculate an average number, but actually there are small fluctuations about that average number. And equivalently, you could consider you could consider uh, a so-called grand canonical ensemble in which the energy of the system, this small box being the system, plus energy of the reservoir is fixed E0, just like the canonical ensemble, and the number of particles in the system and the number of particles in the reservoir is fixed at N0, and there is both particle exchange and energy exchange with the reservoir. The question is, when will this system come reach equilibrium, when both are is allowed? And just to remind you what we did in terms of the canonical ensemble, we basically calculated the number of microstates which are available if the system had energy E1, and if the system had an energy E1, um, the reservoir would have a fewer lesser amount of energy, E0 minus E1, and we maximized the log of the number of microstates of where the system has E1 and this is reservoir has E0 and E1, and that condition, and we could maximize it because we assume that the entire the reservoir plus system, the combined system, is considered isolated, something like a microcanonical ensemble. And then the condition of maximizing the number of microstates for the system and the reservoir, which is a product of the two because they're considered independent of each other, where we neglected surface energy effects. So that gave us a condition that temperature of this and this have to be the same. Actually, it came out in terms of beta, and beta was interpreted later to be 1 by kBT. Similarly, if you do a very similar calculation where both the number of particles and the energy is fluctuating between the system and the reservoir, so then what you do is that with so suppose the system has number of particles n1 and energy e1, and the reservoir has number of particles n0 minus n1 and e0 minus e1, and corresponding to n1 and e1, the number of microstates for the system is omega, and for the reservoir is this quantity, and we maximize the log of this, which is the condition for equilibrium in the microcanonical ensemble. So that's why you maximize the log. And this in turn, if you do a Taylor's expansion, then you would have once a derivative with respect to energy. I mean, we would have a derivative with respect to energy of log omega um, r, and so on and so forth. You will have two terms, and you will neglect higher order terms because you assume that the system is much smaller than the reservoir. And not only will you get beta 1 and equal to beta 2, which is the temperature of the two systems has to be the same, but you will also get del del nr nr of kb log omega r of this and of the reservoir and the system to be equal, and that you later identify with the chemical potential of the system, or rather chemical potential by kbt, right? So basically the system and the reservoir will be in equilibrium when the chemical potential of the two system of this and the reservoir are the same, and of course temperature is the same. So that's the condition for equilibrium, and the chemical potential, or rather chemical potential by kbt, is defined as kb log omega r log nr, right? So where nr has all the particles. So you remember it's a Taylor's expansion. So when this thing is calculated, del kb log omega r nr is calculated, then the reservoir has n particles, and you're looking at deviations from that. So that defines the chemical potential. So that defines the value of the chemical potential, and the system chemical potential has to be the same as that, which means this quantity has to balance out on the condition of equilibrium. Now, there can be various kinds of microstates, right? Just to discuss what kind of microstates can there be, let me discuss this. Now, suppose this is your reservoir with temperature T, and it has particles 1, 2, 3, 6 number of particles, and it can have energy E1, and then this system can also reorganize its particles. So those I have written 1, 2, 3, which is just representative. These are supposed to represent both position and momentum degrees of freedom. And you could have 3, 2, 1 and 1, 3, 2. And all these correspond to a set of microstates where the energy of the system is E1, volume is V1, and number of particles, say just as a representative thing, is 3. But of course, you know this 3 actually represents 6 and degrees of now. Yeah, so a microstate is defined by 6 and degrees of freedom, right? So these are the various microstates that are possible. Now, if you had a canonical system, now then this reservoir would have suppose energy E2, which is greater than E1, and then correspondingly the momentum degrees of freedom, I mean the ways it can redistribute its momentum, would be more, and so the number of microstates which will be available with an energy which is greater than E1 will be definitely more, and you can get a set of microstates, and I've just shown only 3, but of course there will be much more. But now, so this was with just 3 number of particles which was in the system. In the grand canonical system, you can have not only 3 number of particles, 3 is just representative, some large number n, but you can also have 0, and 1 and 2 and 4 and 5 and 6 and 7 and so on and so forth. And for each, so when n equal to 3, for a particular value of E1, you could have different microstates. Moreover, for a different value of E1, you could have all other set of microstates. And for a different value of E3, you would have a different set of microstates, and that is with n equal to 3. Similarly, when n equal to 4, with energy E1, you would have a set of microstates. And now when energy changes, you would have another set of microstates. And when you have energy E3, which is different from E1 and E2, and n equal to 4, you would have another set of, more set of microstates. And similarly, if you go on with n, the number of particles in the system, you would have a huge number of microstates where not only energy can vary. So for a fixed value of energy, you had different microstates. And then when for a different value of energy, of course, the accessing that microstate might be less probable in a canonical ensemble, but again, you have a large number of microstates. And now in the grand canonical system, or grand canonical ensemble, the collection of all microstates, right? What is an ensemble? The collection of all microstates. Now would also correspond where the system has different number of microstates and different values of energy, and a sum over all of these, where energy is changing, number of particles is changing, and a fixed value, and for a fixed value of E1 and a fixed value of n, you have huge range of microstates. But if sum over all those microstates, then you get the so-called grand canonical partition function, which is a function of chemical potential, because number of particles is fluctuating, it's changing. All that you have is a mean number that you can calculate, the fixed volume, and as a fixed temperature. So this grand canonical partition function, and I represent it by GC, is a sum over I, where the number, so over different microstates, where for a fixed value of energy and a fixed number of particles, you sum over all microstates. Then you, for a fixed number Ni of particles, you vary the energy, and correspondingly you sum over all microstates and vary the energy further. It can have different values of energy which it can absorb from the reservoir, and it's a sum over Es, all the possible values of energy that are that is possible for the system to take. And further more, once you have done that for a fixed number of particles, you say, okay, for a different number of particles, again for different microstates, for a fixed value of E, then different values of energy, and for different values of energy Es, you would have large number of microstates. And then now you have also a sum over Ni, the number of particles in the system can change from 0 to infinity, right? And this will be the partition function. You're summing over all possible microstates that are possible with all possible energies and all possible number of particles, which can vary from 0 to infinity. But practically, how many particles will there be? I'm not saying that all microstates are equally probable. The partition function is a sum over all microstates, but what is the probability of accessing a particular microstate? And that will with number of particles Nj and energy Ek, right? That will be the probability of accessing such a microstate will be e to the power minus mu Nj minus, sorry, not minus mu Nj, it's mu Nj, minus Ek into by kBt. So previously you had minus E by kBt. Now you have an extra term mu beta into Nj. Mu beta means mu by kBt into Nj. So that's the probability of accessing a particular microstate, and the principles are very similar to what was there in the canonical ensemble, divided by the grand canonical partition function. And of course, the grand canonical partition function is a sum over I, S, and mu k. Right? So this is the grand canonical partition function. Here I've not added mu k, but it's really a sum over all possible microstates. But of course, with energy Ek and number of particles equal to Nj, you could have a huge number of microstates with a fixed energy. So those would be these and more, right? So if you ask, so this is the probability of accessing a particular microstate. If you ask what is the probability that there are Nj particles in system 1 and the system has energy Ek, then you have to sum over all the microstates which have energy Ek and number of particles Nj. I just wanted to make that clear. So that's the picture we are heading for. And you can also express this alpha. So actually what is equated, when you do this calculation, when you maximize this, you figure out there is some quantity which is equated, which you call it alpha, and you associate minus chemical potential by kBt with alpha. So in terms of algebra, alpha comes first, and that you associate with minus mu by kBt. And then you could also write the probability of accessing a microstate. So there should be a certain mu, whatever, mu corresponding to a microstate, e to the power minus alpha Ni minus beta Es, because alpha already has this beta term, right? So you can write it like this, divided by the grand canonical partition function. There should be a GC here, right? Now you can easily calculate the average number of particles in the system. Yeah, because there is a fluctuation about the average. I mean, just like energy fluctuates, but you can associate just in a canonical ensemble, you associate the average energy of the system with the internal energy. Similarly, the number of rooms, the number of particles that are in this room is an average n, right? And the way to calculate it is sum over all possible microstates. Here I explicitly write mu s, mu for different microstates with a certain value of energy E, S, and Ni. But of course, you sum over all possible microstates, and corresponding to each microstate, the number of particles in that, when that microstate has an I number of particles, into probability of accessing that microstate, which is e to the power minus alpha Ni minus beta Es by ZGC. Here you should have a GC here, right? And this in turn can be obtained. So this Ni can be obtained by taking a derivative with respect to del alpha, right? I mean, so you take a derivative with respect to alpha, you'll get minus Ni. But you want Ni, so you add a minus sign. So del alpha of Z by 1 by ZGC, Z grand canonical, which in turn can be written as minus del alpha log of the grand canonical partition function. So that's how you would get, that's how you will get the average number of particles in the system. And moreover, you can calculate the average energy of the system, and this average energy of the system can be calculated similarly sum over all possible microstates, the energy of the system when it is at a particular microstate into probability of accessing the microstate, which is this term divided by ZGC. And you're summing over all microstates, and this in turn, very similar to this, can be written as minus del beta log ZGC, right? Now you see that here you have minus alpha Ni, right? And the ZGC, the partition function, can also be in that case written as, for a particular number of particles, suppose Ni, you are actually summing over a very large number of microstates where the energy is fluctuating, right? So in that case, the grand canonical partition function can be written as nr to the power 0 to infinity ZF, I'm writing, later I write it as curly Z only. So ZF is e to the power beta mu. So here what is happening? You have a sum over I where number of particles is changing. So I'm just writing that as Z to the power NR, where Z is e to the power beta mu, or equivalent to minus alpha, I mean, e to the power minus alpha into NR. And this is nothing. So you have a sum over all possible microstates with NR particles and different values of energy. And this is nothing but the canonical partition function. So the grand canonical can be written as z to the power nr, sum over nr, 0 to infinity, sum over all number of particles into the canonical partition functions. Later I use the C so that you can distinguish clearly, right? So in that case, now this is the probability of accessing microstates in a smaller system. Probability of accessing microstates in a smaller system with n1 particles in V box is, yeah. So this is probability of accessing a particular microstate. That's why I write P1 star, Q1 star, number of particles N1 and energy E1. So this is not set of all microstates. P1 star, a particular microstate, is e to the power minus beta E1, P1, Q1, N1, a particular value of P1, Q1, N1. Okay, and yes, then you integrate. So here, what is being done is the probability, just for the like the canonical ensemble, where the probability is going to depend upon all the microstates available to the reservoir, and all the microstates getting available to the reservoir is, the reservoir is represented by the Hamiltonian H2. So you are summing over all microstates of reservoir divided by s to the power 3 n2 factorial, where n1 plus n2 equal to n0, and this is the canonical partition function. This is the canonical partition function Z. So I have reminded you, this is C with n particles for the end reservoir. So this is basically the entire system can take a huge no, wait, this should be n1 factorial. So this is okay. So this h to the power 3n1 and n to the power n1 corresponds to, their identical particles. They can be switched over. This corresponds to n1 particles in a particular in the system, right? And so that there's no overcounting. If the particle positions are exchanged, it will be the same microstate. So that is taken care by s to the power 3n1 and n1 factorial. On the other hand, for a particular microstate that the system is in P1, Q1, the probability actually depends upon all the microstates that are available to the reservoir. If you've forgotten that, the reason, please go back. But it's basically the system is fixed, and you're basically summing over all the probability, I mean, all the microstates that the reservoir can take, and this ZNC is the canonical partition function of the entire system with n particles. So this is going to be the probability of the microstate. And then in that case, this quantity is essentially the canonical partition function, because you're fixing that the reservoir has n2 particles. You're fixing that. You're saying n1, p1, q1. So it's the partition function, canonical partition function with n2 particles in the reservoir this is the canonical partition function with n particles for the entire system, and this term is intact. These two contribute to the partition function for the reservoir, which is ZC, canonical partition function for the reservoir, and this is e to the power minus beta E1, right? So partition function with N2 particles in V2. E2 can vary with 6 N2 degrees of freedom. So this is the picture. But remember, so the point to note, but we are calculating the partition function of the reservoir. If you are at temperature T, if you are calculating the partition function of the reservoir, that itself means that the energy of the reservoir can fluctuate. Of course, the energy will remain very close to a certain value E2 bar, but in principle, it can fluctuate, because only if there can be energy exchange with even a bigger reservoir can you calculate the partition function. Of course, when this energy of this reservoir, so this is the system with fixed number of particles, with fixed energy E1, N1, V1, particular microstate, and that is in contact with a reservoir, and that is whose partition function we are calculating here. But the very idea that you are calculating a partition function means that the energy of the reservoir can fluctuate, though large fluctuations are extremely improbable. So most of the time the system will have an energy E2, but it will fluctuate, and which means that it is in contact with even a bigger reservoir, and beta dash decides the temperature of the system, which in turn decides the temperature of this system. So that's what it means. So the probability that this system will be in a particular microstate depends upon all the possible microstates which are accessible to the reservoir when the system is E1, N1, and V1, and that decides the total, the probability that the system will be in a particular microstate. Right. So what we can write, so what did we get? So we got ZCN. So we got ZCN2 canonical, ZCN, and e to the power beta E1, s to the power 3n1, and 1 factorial. So this quantity which you saw, Z canonical partition function with N2 particles upon the canonical partition function with N particles, this can be written as e to the power minus beta, free energy with N2 particles and free energy with N particles, right? So this is for the reservoir, right? And this is with N particles in the reservoir. And why can we write this? Because F equal to minus kBT ln Z, right? F by kBT equal to ln Z, and basically then Z can be written as e to the power minus beta free energy. So that's all that we are using. So if we have that, we are trying to evaluate the difference in free energy, and the way we evaluate the difference in free energy is saying, okay, this is the free energy of the reservoir with n minus n1, which is n2 number of particles, v minus v1, because that's occupying a certain volume v. So these are extensive quantities, hence they can be shared, but of course, temperature is an intensive quantity. So the reservoir and the system needs to have the same temperature, minus F, the reservoir with n particles, and V at temperature T. And then if you do a Taylor series expansion of this thing, then it is free energy NVT. Note, this is capital N, right? So this is N2 number of particles, N minus N1 is N2, del F del N at volume V into minus N1, this N1, del F del V minus V1 here, calculated at N when the reservoir has N particles, plus higher order terms which we are neglecting, minus this Fn. And del F del N is nothing but the chemical potential. So this becomes So this becomes, and del F del V at fixed number of particles is pressure. So this is chemical potential and this is pressure, and hence this term Z canonical with N2 and canonical with N particles in the reservoir becomes e to the power minus beta, and this difference in energy can be written as minus mu1 N1 plus P1 V1, and then this becomes mu by kBT minus mu by kBT into N1 minus PV1 by kBT, right? This beta goes in, and now you have fugacity again, e to the power beta mu into e to the power minus beta P1 V1, right? So that's what you get. Now here I want to emphasize, that the chemical potential is calculated. It's the change in free energy when the reservoir has n particles. So N2 equal to n, the reservoir has n particles, because that's where you are doing the derivative with respect to the, when doing the Taylor expansion, and the volume V2 has to be V. So essentially the reservoir is taking the entire volume, and the reservoir has all the particles in the system. So V2 is V, V is so V minus V1, it's the total volume. You're basically saying that the reservoir has now taken over the entire system plus reservoir, and it has n particles. What is the total number of partition function? What is the total number of microstates to calculate the partition function? So this is to be very clearly noted that N2 equal to n, all the particles, and V2, the volume of the reservoir, is the total volume. And similarly, when del F del V is being calculated, n equal to, well, number of particles in the reservoir is the total number of particles, and V2 equal to V. That's similar to here, and that is equal to pressure, right? So to calculate the chemical potential, you need to have n particles in the total reservoir, which has the total volume V, and when you add a particle, how much is the change in free energy? So I have put in a different slide to highlight this aspect. So the reservoir should have all the n particles and have the entire volume V. With this, what we were started out with is the probability that the system is in a particular microstate P1 with P1, Q1, and N1 and energy E1, and that's e to the minus beta E1. So this is what we had. And this in turn can be written as the e to the power minus beta E1 remains intact, s to the power 3n1 remains intact, n1 factorial remains intact, but this by this is replaced by this term z to the power n1 e to the power minus beta pv1. Why v1? Remember, so this del f del v, there is with a, okay, so with a minus sign is equal to p, right? So hence you get pv1, and this is the difference in free energy which is being substituted here. So that's why you're getting mu by kBt n1 minus pv1 by kBt, right? Because you have this v1 here, we're calculating this difference in free energy, right? And note, I'm again emphasizing that here you essentially have this fugacity, the chemical potential, pressure, beta, etc. properties of the reservoir. And so, though canonical partition function is an abstract quantity, the probability that the system is in a particular microstate, P1 star, PQ1, Q1 star, particular microstate, that's what we started out with N1 particles and E1 particles can be written simply as e to the power beta mu N1 minus beta P V1, right, minus beta E1 upon N1 factorial to s to the power 3n1. So I will end here and then continue from next.